All right, this is Dr. D again. We're coming back for the second video, and hope that you were able to follow along in that first one pretty well. Because of the way I have my camera phone set up, I can't get my face in there for you to see me without some major adjustments to the video. But here is a cartoon picture that a student several years ago gave to me, and he said he thought one of the characters in this cartoon looked like me. So I thought you might enjoy seeing this. E pluribus unum, out of many one. That's printed on our money. So cashier here says, may I take your order? This guy says, Big Mac, fries, large Coke. Same for me too. And this guy, he said, looks like me, ditto. Who says we can't all get along? Well, I guess in some ways that might resemble my appearance. I know this guy has more hair on the top of his head than I do, and mine's turned quite gray. But I thought it was somewhat flattering, and I appreciate that student bringing this to share with me. I thought that was pretty good. So in the close of that first video, we looked at the noble gas notation, and it's just a shorthand way of writing out an electron configuration. And if you remember, I said that the method of doing that is find the element, like iron, and go up one row all the way to the right, and put that symbol in a bracket, and then write the full ending configuration, whatever comes next. So it would be AR in brackets for iron, 4s2, 3d, 1, 2, 3, 4, 5, 3d6 would get us to iron. All right. Well, we also looked at some of the exceptions to Aufbau's predicted configurations. Now, I want us to move on just a little bit. And in your copy, you would be looking at this one, and the next set of notes then would cover your orbital diagrams. And so this is in your handout there. Orbital diagrams use boxes, and these boxes represent orbitals. If you remember in the first video, I said, suppose that you were in a room where there were two chairs sitting at each table, and there was only room for two people at a table. There might be no one sitting at a particular table in the chairs. There might be one person sitting there. Maybe you're sitting by yourself. Or you might be at a table where you and a friend are sitting, but there's not room for any more. So what we're going to do is to use a box to represent an orbital, to represent that table that has two chairs, if you want to think of it that way. So boxes represent orbitals, and then arrows we're going to use to represent electrons. Each S sublevel has one orbital, so therefore it only has one box. P has three orbitals, so therefore we would have three boxes. D has 5, F has 7. Now, if you're wondering where we got those numbers from, let me go back to a previous page. And this was a page about the Aufbau principle. Up here, sublevels S, P, D, and F have 1, 3, 5, and 7 orbitals, respectively. Let's consider or think about oxygen. Oxygen, it has an atomic number 8 on the periodic table. It's right here. Oxygen's configuration would be 1s2, 2s2, 2p1, 2, 3, 2p4. If I wrote the noble gas notation up and over, He in brackets, 2s2, 2p4. So here again is that configuration I was just talking about. When we draw the orbital diagram for oxygen, we'll use one box for the s orbitals. So we have one s, and arrows represent electrons. I'm going to put an up arrow in the box first, followed by a down arrow if there's a second electron in that sublevel orbital. So 1s2, just like that, 2s2, 2p has 4 electrons. I'm going to put an up arrow in each box first. Make sure you always do that, and then put your down arrow. Some textbooks, instead of showing a box, might show a circle with up and down arrows in it. A circle would be fine if that's easier to draw. When placing arrows in the boxes, each orbital of a sublevel must have an up arrow before pairing it with a down arrow. And basically, this is according to Hund's rule, that pairing of electrons in a sublevel will not begin until each equal energy orbital has at least one electron. All right, let's consider the element iodine. Z equals 53. Iodine, like other halogens, are great disinfectants. And as I mentioned in yesterday's video, I'll be having knee surgery here in just a few days, and they'll put betadine, which is a solution containing iodine, over the skin before they begin the surgery. That sterilizes it. You know that chlorine in tablets or liquid form may be used in swimming pools to disinfect it. In a hot tub, they use bromine because that's a good disinfectant. Iodine is a good disinfectant as well. Fluorine we don't use as a disinfectant too much. It's just too reactive and too powerful to be of much common use. So here's iodine. Z equals 53. If I were thinking of the full configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then we run into 4d10, brings us all the way to cadmium. And now we're in 5p, 1, 2, 3, 4, 5, 5p5. The noble gas notation would be up and over. Kr in a bracket, 5s2, 4d10, and then 5p5. I hope you're following along on that. So here's iodine. We have Kr in the bracket, 5s2, 4d10, 5p5. I drew the orbital diagram just for the full ending configuration. One box for S has only one orbital. D has 5 orbitals, so it has 5 boxes. It's filled with 10 arrows, 10 electrons. 5p has only 5 arrows, 5 electrons. We have 3 orbitals, and remember, according to Hund's rule, we've got to have an up arrow in each equal energy orbital before we start to see any pairing, before the down arrows go in. For instance, on the p orbitals, they're sort of dumbbell shaped, but they go along each axis. So if you think of an XY axis, so the x-axis would have sort of a dumbbell-shaped orbital for 2 electrons. The vertical or y-axis, it would be sort of dumbbell in shape, and maybe it'd be better if I just go ahead and draw that for you. So this would be along the x-axis, and let's say the nucleus is right there, and so we have an orbital sort of shaped like that. The y-axis would be the vertical, and again we would have the same thing. And then there's a z-axis. So the x-axis is like that, the y-axis is like that. The z-axis, it's hard to draw on a 2-dimensional piece of paper, but actually that third axis would be coming right out of the plane of the paper if I could demonstrate that 3-dimensionally. It's hard to draw it though on paper, but anyway, so we have a pair of electrons there. Basically, 1 electron at each end. If we merge all 3 of those together, we end up with P looking sort of like the petals of a flower. If you had 6 balloons and you blew them all up to the same size and kind of tied them all together, you'd have a 3-dimensional image of the p orbitals. D and F orbitals are kind of complicated. I won't try to draw those. S orbitals, if you remember, are spherical. They're just circular, just like that. There are 7 valence electrons. Valence electrons are the electrons at the highest energy level. Well, energy level 5 has 2 electrons in S and 5 in P. 2 plus 5 is 7. So 7 valence electrons. They are in 5s and 5p. Within these 7 valence electrons, we have 3 pairs and 1 lone electron. In 5s, we have 1 pair of electrons. Up and down arrows. In 5p, we have 2 pairs of electrons, and then this guy's all by himself, or herself, however you want to call that. The orbital diagrams indicate when 2 electrons are paired or unpaired. All right. Now moving on to electron dot structures, or electron dot diagrams. On your periodic table, I have some of the dots drawn in. Again, I know it's hard for you to see some of this, so look at your piece of paper if you can. Remember I said that this is the S block, these first 2 columns. P block is over here, D block is there, and F block down here at the bottom. In this first column, we only have 1 valence electron for all of these elements. So every one of these has a single dot next to the symbol. That dot represents the valence electrons, the bonding electrons. In group 2A, we have 2 valence electrons. So they have 2 electrons and they make up a pair of electrons. They're both in the s orbital. So it would be like drawing one box with an up arrow and a down arrow in the same box. I'll mention about D in a moment, but let's go to the P block. Now, for instance, on boron, we have a config of 1s2, 2s2, 2p1. So we would have a pair of electrons in 2s and a single electron in 2p. So how would we draw that? Well, let's start here back at the beginning real quick. And I guess I could use this that I had drawn earlier. So for hydrogen, I have 1s1. When I draw hydrogen's dot diagram, I put 1 dot there because it has only 1 electron. Helium, He, has 2 dots. If I were drawing this orbital diagram for 1s, I would have an up arrow and a down arrow. That would be 1s. Lithium, notice it ends with 2s1, so it has 1 dot, just like hydrogen. And if I had gone to number 11 for sodium, you would find it also has 1 dot. I'll go ahead and list that on here. Sodium, this is Z equals 11. And if I do the shorthand way of doing this, that shorter method, the noble gas notation, for sodium, for 1s2, 2s2, and 2p6, the second energy level is full. That would be the noble gas neon. So for sodium, if I go up 1 row and all the way over, I get to sodium, so, neon, and then 3s1 gets me to sodium. So for the noble gas notation, I'll just put Ne in a bracket, and then the next electron is in 3s1. So for sodium's dot diagram, I got 1 dot, just like lithium and hydrogen. All right, beryllium has 2 valence electrons. So beryllium has 2 dots. Boron has 2 electrons in 2s and 1 electron in the p orbital. So boron has a pair of electrons in s and then a single electron in p. For carbon, I would draw this. Oh, whoops. I make mistakes sometimes. Sorry, folks. Carbon is just capital C. And usually I'll show it as 2 dots together because the 2s electrons are a pair, and then 2 single dots. However, some textbooks or some teachers will just draw it like this, because when carbon is forming 4 covalent bonds, they're pretty well equally spaced out. For nitrogen, we've got 2 plus 3, that's 5 electrons. So we do have 1 pair of electrons and then 3 single electrons. Oxygen has 6 valence electrons, 2 pairs and 2 single electrons. For fluorine, we have 7 valence electrons. So 7 dots. Neon has 2 plus 6, that's 8 valence electrons. And so that's 4 pairs of electrons. And then we get sodium. So what I suggested here on the electron dot structure page, identify the configuration for Z equals 34. That's the highest n values. The ending configuration is the biggest energy level number. Here's the full config, and when you look at the full config, I see some electrons in the 4th energy level at 2 places, 4s and 4p. So the full ending configuration is where I would cover up everything that would relate to argon, AR in a bracket, 4s2, 3d10, 4p4 would be the full ending configuration. 2 and 4s plus 4 and 4p, there are 6 valence electrons. So, for Z equals 34, the element is selenium. The element symbol represents its nucleus and all the inner electrons. Use dots to represent the valence electrons. So Se, and because I have 2 plus 4 more, or 6 dots, 6 electrons, I space them around the symbol like this. If you happen to notice, selenium is just like oxygen and like sulfur. So I was showing you this a little while ago. For boron, I had 3 dots. Carbon, 1, 2, 3, 4. Same thing for all the ones underneath there. Nitrogen, 1, 2, 3, 4, 5 dots. Same thing for phosphorus and arsenic and so on. And here's oxygen with 6 dots. You can see those 6 dots, 2 pair and 2 single ones. Same thing for sulfur, and selenium, the same thing. So there are 2 dots there. This is not drawn on your periodic table copy, I don't think. And you could always add it. So 6 dots, 6 valence electrons. It's in group 6A. It's an easy way to think of it. The halogens, I showed you fluorine's dot diagram a few minutes ago, 7 dots. And then neon, 8 dots, 2 on each of 4 sides. All right, so determine how many electrons or dots by adding the superscripts in the valence ending configuration, then determine if they're paired or unpaired. And you can use the orbital diagrams to decide if they have a pair or not. So if we did the orbital diagram for selenium, and let's say, just for the sake of time, I'm not going to do the D arrows, but we have 4s2, so we have an up and a down arrow. And then 4p4, remember p has 3 orbitals, and it's okay to connect the boxes together. It's a little easier for me. 4p4, first arrow goes in like that. There's the second, there's the third according to Hund's rule, and now the 4th electron, the last electron, is that down electron there. That's for 4p. So a pair of electrons are shown as 2 dots above, below, or on either side of the symbol. Unpaired electrons are shown as single dots in any of those 4 locations. Usually you don't have more than 2 dots per side of the symbol. So there's a pair, and these are unpaired, or what we sometimes call lone electrons. Just remember, the number of dots equals the number of valence electrons. What about for Z equals 27? The full configuration or ending configuration, 4s2, 3d7. Look for the highest energy level number, 4. There are only 2 electrons there. They're both in the s orbital, so they are a pair of electrons, just like those. And so we draw 2 dots together for cobalt. I didn't mention this D block before as far as the dot diagram, so I told you I'd come back to it a little bit later. There's cobalt, Z equals 27. Most of these are going to have 2 dots. Remember though, chromium is an exception, and copper and silver and gold, and there are others as well. So when you're drawing dot diagrams, to indicate the number of valence electrons, you might need to refer to a list or some sort of diagram. The F block usually just has 2 dots as well. These all are somewhat of an exception to the off-bar diagram between the D and the F sublevels, and sometimes including the S, but we're not going to get into it that deeply in this class. All right, I need to move on. This next one covers 2 sheets on this particular page, and I think I told you it might be wise to write the quantum number notes where you put part of it up above the fold or the staples of your flip chart and then the other part below. But this section right in here on your notes is where I'm at right now. So here is an example, or this is an example of a quantum number. 4, 2, -1, +1/2. It's sort of like the address for the element's last electron. So the N number, that principal quantum number, is there. L is the sublevel identification number. ML is the orbital, and MS is the spin of the electron. So I don't think we got to these notes at all in your flip chart. You know, this is new material for you. So N is the principal quantum number. It describes the size of the energy level. Now, energy level 2 is bigger than energy level 1, but it's smaller than the 3rd or 4th, and so on. It identifies the energy level and ranges from 1 to 7. L identifies the sublevel, describes its shape, and ranges from 0 to n-1. So the given values are, if the sublevel is S, the L number will be 0. You know, the L number would be in that second position. If the electron is in the P sublevel, then L equals 1. If it's in the D sublevel, L is 2. Well, notice this is 2. That tells me that this electron is in the 4th energy level and the D sublevel. D equals 2. And if it's in the F sublevel, then L would be 3. Remember, S is spherical in shape and P is dumbbell in shape. ML identifies the orbital, its orientation in space, and ranges from -L to +L. So what we do is use the orbital diagram to figure out the value of ML. So this one says -1. It's in the D sublevel, and D has 5 orbitals. Here's the D sublevel. So 0 is a value for the center box always. ML, use the orbital diagram to determine ML. The center box is always 0. So if this electron is in the -1 position, that means that it is an electron in this box right here that has a -1 value for the D orbitals. MS is the spin. It's +1/2, so I'm getting a little ahead of myself, but that would be an up arrow in that box. So if that's the last electron, then that means that this D has only 2 electrons. 1 up arrow there, 1 up arrow there. 4th energy level, D sublevel. I could write that as 4D. And then -1 box, it's an up arrow. 4D2 would give me a hint as to the identity of that element. So I know I'm getting a little hit of where I stopped at the notes, but let's go ahead and look at this. In the 4th energy level, remember I said that D is 1 number behind, so this would be 3D, so that can't work. In the 5th energy level, after 5S comes 4D. So 4D2 would bring me to zirconium. That should be this element with that quantum number. Now, we'll look at how we figure that out a little bit later. So here's the last part of the notes then. MS, and remember again we had those 4 values, N, L, ML, and MS. MS identifies the spin. It's either +1/2 or -1/2. You know, chemists would look at it, the spin is either clockwise or counterclockwise, depending on your point of view or your position when you're looking at it. So an up arrow in the orbital diagram would have an ms value of positive 1/2. We always put the first arrow in as an up arrow in the box. A down arrow means the ms value is negative 1/2. According to the Pauli exclusion principle, electrons in the same orbital must have opposite spins. Therefore, no two electrons in an atom can have the same set of 4 quantum numbers. So if you think back of the orbital diagrams that we looked at before, let me back up a couple pages here. Like this, we have 10 electrons in 4D. Notice that I never will have 2 arrows pointing in the same direction in the same box. That's Pauli's exclusion principle. That was one of the chapter 5 vocab words that you had as well. All right, so let's go back here. Write the quantum number for Z equals 22. So on the periodic table, Z equals 22 is titanium. So we should hopefully be familiar now with reading a configuration from the periodic table: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I've got to go over 3d2 to get to titanium. So it ends with 4s2, 3d2. The last electron would be 3d2 to go into position. So here's the full configuration. The last electron is there. It's in 3d2. So I'll write the quantum number for this. The energy level is the third energy level, so n equals 3. It's in a d sublevel. So if you remember for the L value, that if it's in the S sublevel, S equals 0, P is 1, D is 2. So I write 2 for the L, 3d2, and then I need the orbital diagram in order to figure out ML and MS. So for 3d2, D, remember, has 5 orbitals. Remember, the center box is always 0. And we also said that ML ranges from negative L to positive L, negative 2 to positive 2. Center box is 0. If this last electron is 3d2, my first electron would be an up arrow there, and the second electron would be an up arrow there. So the ML value is negative 1. That's where I get this from. The last arrow that I put in the diagram. And it's an upward pointing arrow, so it's positive 1/2, just like we set up there in the notes. Always show the sign for the ML and MS values except for ML equals 0. There is a good quantum number video that you might want to check out on YouTube. I'll leave this there if you can hold it up there if you want to copy down that YouTube URL. So we didn't even get to the point of decorating the front cover of your flip chart. That's all right. You could pause the video if you need to continue copying that down. So that really brings us to the end of the flip chart. And that brings us to the end of that page. And with that, I'm going to sign off on this video. And I hope things are going well for you. Talk to you later.